Okay, my dear students, let's move to the next lecture. Let me remind you that you must get a copy of my notes from the Photoshop outside the department because the notes which I am displaying in these videos may be very dim, but if you have those notes before you, and when I mention about any particular page, you must turn to that page and then watch this video. You will be able to follow what I am saying. Okay, so we in the previous lecture we finished with the derivation of the generating function and the Rodrigues formula for the Legendre polynomials. I told you the utility of the generating function. In fact, in today's lecture we will apply the generating function of Legendre polynomials to deal with a very important problem of electrodynamics, and then you will see how useful is the generating function. The Rodrigues formula is in fact used to calculate a particular Legendre polynomial being a solution of the Legendre differential equation of a particular order. Okay, so let me first display a page from the book by Arfken. This is the third edition of Arfken, and this is the page number 638. I want to start with, rather 637. Here is the generating function written somewhere, and this is in fact the electrostatic potential of a monoelectric charge as shown in this diagram. You see that the charge is placed at origin, and we have to find, the charge is placed at a distance on z-axis with z is equal to a, and we have to find the electrostatic potential at a point P which is distant r from the origin and which is at the distance r1 from the charge. And we know the electrostatic potential using Coulomb's law, phi is equal to q over 4 pi epsilon naught into the distance of the point from the charge, which is r1. Okay, we will apply the generating function given by equation 12.4 which we derived in our previous lecture to obtain the value of the electrostatic potential and we will reach to this result given by equation 12.3. Now if I look at 1 over r1 from this diagram and apply the cosine law, which you know that r square is equal to r1 square plus z square minus 2 r1 into z into cosine theta. So this is the cosine law which has been written here, which has been used here for writing the value of 1 over r. So this is r square plus a square minus 2ar cos theta power minus half. So you will immediately feel that this expression is quite close to the generating function of the Legendre polynomial, which is this one. Well, I showed you. Okay, this is 1 over minus 2xt plus t square power minus half is equal to Legendre polynomials Pnx into t to the power n with n changing from 0 to infinity. Okay, so this expression is quite similar. So when we use this the knowledge of the Legendre of the generating function. Now this I have done at page number sorry, let me confirm the page number from my notes, which you will consult for what is being said here. This is page number 6, I think. No, it is page number 5. Let me display this page so that you can have a look. Well, this is page number 5. Let me put it upside down by rotating this page. Okay, so you can see the use of the generating function over for this situation as shown here. So it is quite dim, but if you have the original notes with you, the original copy of the notes, you can easily see what I want to say. So here is the application, and you will reach to this result from as shown by equation 12.3 from the book by Arfman. So you will ultimately see that the electrostatic potential is given by this expression. So here is the use of the Legendre polynomials. We have substituted cos theta for x, and we have substituted a over r for t from the generating function of the Legendre polynomials to reach to this result. So this is the electrostatic potential of this diagram, in which there is a single charge placed at the distance z is equal to a, and the potential is being evaluated at this position. Okay, now the beauty of this application of the Legendre of the generating function of the Legendre polynomials, you will see that if we now move on to a electric dipole, and here is an electric dipole, a charge equal to minus q placed at z is equal to minus a, and a charge plus q placed at z is equal to a, and the electrostatic potential being evaluated at a position r from the origin, and the potential is obviously equal to q over 4 pi epsilon naught into 1 over r1 minus 1 over r2. So this expression in the bracket will now be evaluated using the generating function of Legendre polynomials. And for this, I would suggest that you turn to page number 9 of my notes. Let me bring this page before you, although it is quite dim, but with the original notes you get from the photocopy shop, you will be able to follow this derivation, and you will see that the result comes out to be equal to let me show you the result. Right, so this is the electrostatic potential, in which this is the value of 1 over r1 and this is the value of 1 over r2, the second term, and using the generating function of the Legendre polynomials. Here we have minus sign, as is the situation shown in the. So we will say that this is the electrostatic potential due to a dipole. Okay, 1 over r1 minus 1 over r2 as calculated using the generating function, as applying the generating function on the present situation, and you will see very easily from the detail given at page 9 and 10 of my notes. You will easily derive this expression 12.10, that phi is 2q over 4 pi epsilon naught into r multiplied by p1 cos theta a over r plus p3 cos theta a over r cube, and so on. So the approximation result with r much larger than a is given by this, because when r is much larger than a, obviously the higher order terms will be neglected, and we will limit ourselves to the first term, in which it is, so the result will become as 2aq over 4 pi epsilon naught into p1 cos theta over r square. So here 2aq is in fact the dipole moment of the dipole. So if you look at this result, if you focus at this result, this is the same result you might have obtained when you were calculating the electrostatic potential due to a dipole in your course on electrodynamics. Okay, so we have achieved the same result, equation 12.11, using an approach through the Legendre polynomials. So Legendre polynomials have a very beautiful application here. Rather, the generating function of the Legendre polynomial is being used here to reach to this electrostatic potential due to a dipole. Now we can further extend this result to a more complicated situation, in which we have, so this is the diagram which I mentioned before, and now let me move on to this combination of 4 charges. Charge plus q placed at z is equal to minus a, charge plus q placed at the position z is equal to plus a, and a charge minus 2q placed at the origin. So this combination of 4 charges, 1, 2, 3, 4, makes a linear quadrupole, and we can find the electrostatic potential due to a linear quadrupole. Here it is given as an exercise 12.1.1, but you can see this derivation at page 9 and 10 of my notes very easily, and you can find the electrostatic potential due to a linear quadrupole given by as an answer to this. And this is a further extension. Here we have a linear octopole. So now we have 2 quadrupoles placed side by side, and we have calculated the electrostatic potential due to an electric octopole. So you see the Legendre polynomials, and this is also done in my notes. I think it is at page, let me give you the page number where you can evaluate the this is page number 13, in which this exercise is solved, and you will find the electrostatic potential due to an electric octopole, okay, linear octopole. So if you would have asked to calculate the potential due to a combination shown here in figure 12.6 using the conventional procedure of electrodynamics, it would have been very difficult. So you see the utility of the generating function of a Legendre polynomial and the applications of Legendre polynomials playing their role in solving a physical problem. Okay, so that is the electrostatic potential due to an electric octopole. And mind you that once you find the electrostatic potential, you can go on and find the electric field due to these combination of charges, and this you will also find from my notes the calculation of electric field intensity once you know the electrostatic potential due to any figure. Okay, now exercise 12.1.3, here it is said that if R is not greater than A, but if R is less than A, then the potential is given by this expression. Now this is a situation in which the distance of the point from the center of the dipole is much less than the separation between the charges of the dipole, and this exercise has also been solved in my notes, and you can go through my notes and solve this exercise and get this result. I would also suggest that you also solve the exercise 12.1.4, and this is the same thing I mentioned just before, that electric field intensity to be evaluated once you know the potential by this expression that electric field intensity is minus gradient of phi. So when you take the gradient of phi using the spherical coordinates, you will see that this is the electrostatic potential due to a dipole, and the three components of the electric field, the radial component, the theta component, and the phi component, comes out to be like this using this expression, that E is equal to minus gradient of phi, where gradient, the value of gradient will be used from spherical polar coordinates, and this exercise has also been solved in my notes. So you must go through these exercises I have mentioned and complete this discussion on the generating function, the Rodrigues formula, and the application of the generating function in calculating the electric potential and the electric field intensity due to a monopole, due to a dipole, due to a quadrupole, and due to an octopole. So I think for this lecture this is quite sufficient. If you can do these derivations by your hand with the help of my notes, and that will be the today's lecture. Okay, thank you very much, and next time I hope we will meet after your midterm examination, if they are to be announced, and if not, then we will continue our discussion to the further topics on Legendre polynomials. Okay, thank you very much.